Look, whether you're a junior mechanic just stepping into the workshop or a greenhorn engineer trying to figure out why your parts keep literally breaking into pieces, gather round. I've spent decades down in ship engine rooms and under hoists and garages dealing with this invisible, totally physics-bound force that just routinely destroys rotating assemblies. It is the silent killer of drivelines, and honestly, by the time you can actually feel it, it might already be way too late.
Okay, so let's dive into this by defining what we're actually up against here. Every single rotating shaft has a natural frequency, right? Critical speed is simply the exact RPM where the rotational speed matches that natural frequency, causing the resonant amplitude to spike exponentially. Think of it exactly like pushing a kid on a playground swing. If you push them at random, chaotic intervals, the swing barely moves. But if you push at exactly the right rhythm, that swing arcs higher and higher. The drive shaft behaves the exact same way. Critical speed isn't some manufacturing design flaw, it's an absolute physical law.
And this swing analogy brilliantly illustrates why things go so wrong, so incredibly fast. I mean, why does a tiny, microscopic 1 millimeter wobble completely tear apart a heavy-duty truck? Well, it's because as you approach that critical speed, centrifugal force takes that tiny eccentricity and just amplifies it. The deflection increases, which then increases the centrifugal force even further. It's a vicious, self-reinforcing loop. Near critical speed, that tiny wobble mathematically trends toward infinite deflection. The shaft will literally bend violently and fragment into flying shrapnel within milliseconds. It's wild.
To truly understand how to diagnose and prevent this from happening, here's our roadmap for today. We're going to cover the rhythm of destruction, calculating safety margins, material wars, specifically carbon versus steel, real-world catastrophes, a dive into marine systems, and finally, the exact workshop diagnostic workflow you need. All right, part 1, the rhythm of destruction. Let's prove the theory with some hard numbers. Get a load of this staggering number, 70,519 RPM. This is the calculated critical speed of a standard 45-inch passenger car steel drive shaft, exactly like what you'd find in a short wheelbase truck. Now, why on earth is it so high? Because critical speed drops with the square of the length. Short shafts are incredibly stiff relative to their mass, which means they can safely rev to numbers way, way beyond what any vehicle engine could ever actually produce.
Now contrast that critical speed against a typical engine redline of, say, 5,500 RPM, and you'll see you've got a massive 12.8 times safety margin there. And this brings us right to the golden rule of driveshaft engineering. You absolutely must always maintain at least a 20% safety margin between your maximum operating RPM and your critical speed, because as you'll see in a minute, real-world wear and tear eats into that 20% margin remarkably fast.
You know, you might be wondering why we use hollow tubes instead of solid bars for these drive shafts. Well, I can tell you right now, it is definitely not just to save a few bucks on steel. Critical speed improves with higher stiffness and lower mass. A hollow shaft actually drops up to 60% of its weight while retaining nearly half the stiffness of a solid bar. So by optimizing that stiffness to weight ratio, hollow shafts drastically raise the critical speed per kilogram. Pretty clever, right? Moving on to part 2, material wars. Trading ductility for absolute stiffness. Let's look at how changing the material completely rewrites this equation for the exact same vehicle. Okay, let's break down the numbers here. Look at steel on the left. High density and high stiffness, giving us a critical speed of around 8,900 RPM for our example length. Aluminum, well, it's a lot lighter, but it drops significantly in stiffness, which actually results in a lower critical speed of 7,200 RPM in this specific scenario. But then, look at carbon fiber. It combines a super low mass with an incredibly high effective stiffness, rocketing that critical speed all the way up to 14,200 RPM. It decisively beats both metals, giving you a 59% higher critical speed while dropping the rotational mass, a real game changer.
But hold on, there is a massive, dangerous trade-off here. Steel is ductile, meaning it yields and bends, right? That causes a progressive vibration that warns the driver well before an actual failure. Carbon fiber, on the other hand, is completely brittle. A simple stone chip bouncing off the road or a slight impact can cause internal delamination that drops that critical speed instantly. It gives absolutely zero warning before it just shatters into sharp fragments. And this is exactly why carbon fiber requires highly specialized, scheduled internal inspection protocols to keep you safe. You can't just eyeball it.
Section 3. Real-world catastrophes. When theory breaks metal.
Let's look at some actual workshop war stories where that vital 20% safety margin was quietly, secretly eroded away.
Let's start with the long wheelbase van. A center bearing splits a really long shaft into two short, safe shafts. But what happens when that rubber isolator completely collapses? Well, the shaft sags 14 millimeters. That sag essentially joins those two sections together dynamically, drastically increasing the effective unsupported span. Because of that, the critical speed plummets from a massive 94,000 RPM all the way down to just 27,000 RPM. Let that sink in for a second. Suddenly, at normal highway speeds, those normal RPMs amplified that new eccentricity, and the resulting vibration literally shattered the U-joints.
Next up, we have the classic lifted 4x4. The owner fabricated a shaft that was 165 millimeters longer than stock just to accommodate the lift. Well, by increasing the length, they drastically dropped the critical speed. On top of that, they had a tiny 1.2 millimeter weld runout. So when they hit 110 kilometers per hour, the shaft hit 95% of its new, much lower critical speed. That tiny runout amplified catastrophically. The shaft separated, dropped right to the road, and literally pole vaulted the truck. Guys, any shaft extension is a full engineering redesign, not just a quick Saturday welding job.
And here is one that really sneaks up on you. A race team changed their final drive ratio to get better acceleration off the line. They didn't even touch the drive shaft. But the new gearing meant the drive shaft had to spin 12% faster at the exact same road speed. Without realizing it, their safety margin was secretly eroded from a perfectly safe 24% down to just 11%. On a long straightaway, they hit 97% of the shaft's critical speed. The shaft deflected, smashed into the transmission tunnel, and exploded, causing a 200 km/h crash.
All right, Section 4, Marine Systems. Time to jump into the deep end with lateral, torsional, and axial analysis.
So, stepping out of the garage and onto a ship, things get wildly more complex. Marine engineers don't just worry about the shaft bowing out in the middle, which is what we call lateral whirling. Because of the massive forces pushing these ships, the propulsion systems suffer from three distinct resonance modes. First, there's the lateral bending we just talked about. Then there's torsional vibration, where the shaft actually twists and untwists against the massive inertia of the propeller in the water. And finally, there's axial vibration, where the propeller thrust pulses literally push and pull the shaft fore and aft. All three of these have their own unique critical speeds that have to be calculated.
So how do they keep track of all this? They use what's called a Campbell diagram. You map the shaft RPM along the bottom and the frequencies up the side. The horizontal lines represent the natural structural frequencies of the ship's hull and its bearings. The diagonal lines represent excitation forces, things like the engine firing orders or the propeller blades passing through the water. Anywhere a diagonal line crosses a horizontal line within the ship's normal operating RPM range, boom, you have a massive resonance risk that can wipe out a bearing in a matter of hours.
Let's look at a practical example. A ship's aft stern tube bearing operates entirely underwater, constantly supporting the massive weight of the propeller. Listen closely here, because as this bearing naturally wears down over years of service, the shaft centerline physically drops. This subtly increases the effective, unsupported span of the shaft inside the hull. And, just like we learned earlier with the van, longer spans mean lower critical speeds. This is exactly why marine classification societies strictly mandate precise stern tube bearing measurements during dry docking.
Section 5, the workshop diagnostic workflow. Let's find the fault.
Okay, let's bring it right back to the garage. If you're a mechanic hunting down a driveline vibration, here are your strict marching orders. Step 1, always convert the road speed where the vibration happens into actual drive shaft RPM using the tire size and final drive ratio. Next, visually inspect those center bearings for any sag. Then, grab your dial indicator and measure mid-span runout. Honestly, anything over 0.5 millimeters is borderline and needs your attention. And to finish up, verify the U-joint phasing and operating angles using an inclinometer. Pay special attention to lifted chassis where the pinion angles have been messed with.
You'll definitely want to keep this diagnostic decision tree in your back pocket. If the vibration occurs at a fixed road speed, regardless of what gear you're in, your primary suspect is either the drive shaft or the wheels. Now, if the vibration strictly follows the engine RPM, suspect the engine mounts or the transmission. And if the vibration only kicks in under hard acceleration but smooths right out when you're coasting, you're almost certainly looking at a failing U-joint or a worn slip yoke reacting to that load.
Look at this quote on the screen. It really sums up the whole shebang today. Imbalance doesn't cause critical speed. The physical dimensions of the shaft cause it.
But as you get near that critical speed limit, even the tiniest bit of imbalance becomes totally catastrophic. This is exactly why simply balancing a shaft will never fix a critical speed issue. And it's why you must absolutely respect that 20% safety margin. It is non-negotiable.
So I'm going to leave you with this thought. The next time you're driving, or maybe testing a customer's vehicle, and you feel that deep, resonant boom and vibration at exactly 62 miles per hour, a vibration that magically goes away at 67, ask yourself, is it really just a bad patch of road? Or are you bumping right up against the invisible physical limit of that vehicle's drive shaft? Start looking at the machines around you with an engineer's eye. Check those support bearings and absolutely never take those safety margins for granted.